welcome back to this final installment for this mini course on topological four manifolds. Slight change of format today, but okay, let's get started. All right, the plan for today is to quickly recap the main things that we've done so far, have a bird's eye view of the things we did not talk about, and then also say a little bit about what are some open problems, what are some other things that people are thinking of, and maybe try to convince you that you too could be thinking about topological four manifolds. Maybe you already are. Okay, so what have we done so far? So in the first two lectures, we focused on this result of Friedman, that if you have smooth, closed, oriented, simply connected four manifolds, there's fours over here, then isometric intersection forms imply homeomorphism. The first step of that was due to Wall, but the sort of key insight there was due to Friedman regarding his proof of the Escaportism theorem in this dimension. So the main tool here was the Escaportism theorem. And the idea of the proof of the Escaportism theorem was really inspired by the high dimensional proof by Smil, where we looked at a Handel decomposition of an Escaportism and we manipulated it until it became trivial. You know, for many of us, maybe that are not used to thinking about higher dimensions, this may seem kind of random, but it really does belong in this larger story when you expand and think about high dimensions. So that's where this first theorem came from, seeing what we could do with these high dimensional tools in this dimension 4 or 5-dimensional cobordisms. And then in the live lectures, we focused on these results of Quinn, and in particular, the result that we focused on is this one, that if you have a connected, non-compact, again, four manifold, it's smoothable. And then once again, the techniques that went into this proof, they're part of a larger story. The main idea here was this notion of Handel smoothing. And again, this is something that was extremely successful in high dimensions. And then the sort of slogan for Quinn was, let's see to what extent we can apply it in dimension 4. These are sort of very natural things to try. All right, so if you're taking nothing else away from this mini course, I hope you'll take away the statements of these two theorems. Ideally some more, but these two for sure, okay? So I want to talk a little bit about this first theorem on the slide here. So this is extremely close to a classification result. So let me go ahead and state it. So this has come up a couple of times, I think, maybe most notably in Paul Mellon's talk. So Friedman and Quinn, their work together gives you this following classification of closed, simply connected topological four manifolds. Andras mentioned this in his first talk to us, I guess, and throughout his series. This statement says that if you have an intersection form, essentially, so you have a symmetric non-singular integer bilinear form, maybe represented by a square matrix, depending on the parity of that form, there are precisely one or two homeomorphism classes of four manifolds representing it, closed, simply connected, oriented. In the case of even intersection form, there's precisely one, so it's unique up to homeomorphism. And then if the form is odd, there's two of them. I'm calling them M and star M. They both have the same intersection form theta, but one of them has trivial Kirby-Sieben-Min invariant, whatever that is, and the other one has non-zero Kirby-Sieben-Min invariant. Kirby-Sieben-Min takes values in Z mod 2Z, so these are the only two possible values. So why did I say that we're very close to this? We've actually seen virtually every part of the proof of this at this point. So let me talk about how that works. Well, the uniqueness of this is basically the Escaportism theorem. Okay, so in the case of smooth, closed, simply connected, oriented four manifolds, this uniqueness that was part of that classification result, that's really just coming from the Escaportism theorem. you have to wonder about what do we know if you just have topological four manifolds. Well, then you need the topological Escaportism theorem. Well, we also talked about that, but we have it. So the uniqueness aspect we've talked about quite a bit already. I hope that makes sense. This is saying that if you have manifolds with the same intersection form, and in the case of odd intersection form, the same Kirby-Siebelman invariant, then you produce for yourself an Escaportism, and then these Escaportism theorems tell you that those Escaportisms are trivial, and therefore the two ends of them are in fact homeomorphic. So uniqueness is something we've spent quite a bit of time thinking about, actually, even if not necessarily in those words. And then existence actually came up yesterday. So yesterday I gave you a sketch of a proof of this quite wonderful result of Friedman, that if you have an integer homology three-sphere, then it's the boundary of a compact contractible four manifold. And so this gives a very nice way of constructing topological four manifolds with a given intersection form. So for example, I guess Andras mentioned this, or, oh no, actually, I think Paul mentioned this. So for example, if we have this thing called the Chern manifold, which is star CP2, well, star CP2 has the following construction. I'm going to start with B4, so that's B4 over here. And I'm going to attach a two handle along the right-handed trefoil with framing plus or minus 1. Oops. Okay. Let's say plus 1. And then the boundary of this thing that I've constructed so far, this boundary looks like, oh, that's the wrong trefoil. This boundary looks like this. I mean, that's the picture of the four manifold, but also the picture of the three manifold boundary, as we know from Lisa's lectures. And so this thing is an integer homology three-sphere, as in the homology of this three manifold is the homology of S3. And what Friedman tells us is that this thing is the boundary of a contractible four manifold. So I can use that to cap off this thing. And this, at the moment, I've built for you a closed four manifold. It's only topological because of this contractible piece C over here. But it has intersection form plus 1, and that's coming from that plus 1 in this construction over here. And one way to see that you've built star CP2 instead of just CP2 is because we used the right-handed trefoil in this construction rather than, for example, the unknot. And then there's a precise way to sort of determine this sort of thing.
So the left-handed trefoil doesn't have like the right, what is it, like ARF invariant or something?
No, it does. So I just wrote RHT, so I wanted to.
So you just wanted to be consistent. Okay.
So in general, any K with ARF invariant 1, whoops, will produce star CP2. And if you use a knot with ARF invariant 0, it will produce the usual CP2 up to homeomorphism. But good question. Yeah, I just wanted to make my, this is a common problem of mine to draw the wrong trefoil. Trying to kick the habit. What I wanted to say is that I gave you the example of star CP2 just because we had heard that name before, the Chern manifold. But you can also use this to, for example, construct a closed, simply connected topological four manifold with intersection form the E8 matrix by first starting off in this smooth side. Instead of having a single two handle, you take the E8 plumbing, so plumb together some disk bundles over S2 with right sort of pattern to get for yourself your desired intersection form, and then you cap it off by this thing. So this existence portion, that's the reason I was talking about this theorem yesterday. Okay. Thoughts about this so far? Okay. So maybe worth noting, when in Friedman 82, he did not have the fully topological Escaportism theorem, and that's why I'm citing Quinn for this classification result. That's where that's coming from. All right, so this is sort of going back to Friedman and Quinn back in '82. So what has happened since then? Let's see if what else is going on. There's several other classification results. I'm not going to go through this whole list, but in the case of closed oriented manifolds, here's several people that show up here. I kind of want to make I don't know, non-mathematical point, which is that some of these years are not that far back in time. So I admit freely that everything that I talked about in lectures 1 to 4 was back in the 80s when some of us were probably not even born, but it's not all like that. There's things that are happening that's relatively recent. This I think is part of a theme. For me, before I started thinking about topological four manifolds, I had the impression that, topological four manifolds is finished if we just know all the things. And these classification results are kind of part of that story, I think. I saw the simply connected thing and I thought, oh, well, we know just a lot. And in particular, maybe there's not much else to do. But I think that is not at all the right way to think about this. And that's part of what I've learned in these last few years. So for example, if we go just a little bit further over to the case of compact manifolds, four manifolds with non-empty boundary, there's virtually nothing that we can say about it, okay? So in the case of simply connected four manifolds with boundary, there's work of Boyer that tells you how to classify them, and you have to sort of pay attention to the boundary when you do this. And in the case of infinite cyclic fundamental group, that is an extremely recent year where we learned something about that classification. And I think the point here is similar to what Lisa has said in her lectures, that, you know, in her case, having the boundary is helpful because there's a place where you can find some more obstructions. But in the case of classification, the boundary is kind of difficult to deal with because that's a place where interesting stuff can happen. So it kind of works against us in this case. But this is an extremely short list, okay? There's so much more that people could try to do here. So I think this notion that, oh, we know everything there is to know about topological four manifolds, there's really no, that's just not true. Okay, yeah. And I would say that this case of non-empty boundary, that's a great place to look at for interesting problems that have not been attacked. Okay. There's another theme here in these classification results. This is sort of telling us of a flavor of the results in this direction, is that you should compare these with what we know in the smooth category. And that's what Andras and Lisa have been telling us about, is that, you know, smooth four manifold topologists and topological four manifold topologists, they should really be working kind of hand in hand. Like the topological results are providing context for the smooth results and vice versa. So these fields are not so disparate or far apart. Like they're really meant to be working in concert with each other, right? So here are a bunch of classification results in the topological category. Smooth manifold topologists, go and find some exotic phenomena given this context. There are other questions that are in this vein. I'm not going to spend too long talking about this, but you might ask questions like, you know, when are homeomorphisms of a topological four manifold isotopic? And then once again, some of these years are relatively recent years or extremely current years that people are thinking about this sort of question. So maybe to say something about this, in Quinn's work from 1986, he showed that homeomorphisms of closed simply connected four manifolds up to isotopy are determined precisely by what they're doing on the intersection form. And then once again, there's a very natural question of asking, well, what can you say when you have non-empty boundary? And like I was saying, like the non-empty boundary case is not something that people have spent a lot of time thinking about, but they should. And there's lots of cool questions there that are worth thinking about. And in this case, Patrick and Mark are doing so. Another thing that you might think about is, well, okay, homeomorphism and diffeomorphism are interesting equivalence relations, but maybe we should think about some others. For example, what are some homotopy equivalent manifolds that are not homeomorphic? We already saw this example of CP2 and star CP2. They have the same intersection form. They're in fact homotopy equivalent, but they're not homeomorphic. In this case, star CP2 is not smooth, but CP2 is smooth. But it turns out you can also have smooth four manifolds that are homotopy equivalent, but not homeomorphic. And sometimes you can have arbitrarily many families of arbitrarily large size that are all homotopy equivalent to one another, but they're not pairwise homeomorphic. So there's lots of these sorts of questions that one might ask, questions that you have perhaps seen before can arise, for example, in the context of knot theory. Here's a result that I suspect many of you have seen before, and I think it was mentioned this week for sure. For example, we know that knots with Alexander polynomial 1 are topologically leastless. This is something I wanted to spend some time talking about this because we also basically saw a proof of this, just almost as an afterthought. So this, I'm not going to go through this again. This is just meant to jog your memory that yesterday we constructed this contractible four manifold bounded by an integer homology sphere. S3 is an integer homology sphere. So one could try to do this sort of construction. It's a bit silly because S3 cross interval does not have any anything to kill here, right? You can literally build the cone on S3 and that's not very interesting. But if you have an Alexander polynomial 1 knot, you can take in S3, you can take the product of the Alexander polynomial 1 knot with the interval inside of that initial puzzle piece. And then in that construction that I outlined yesterday, you could try to do that entire construction away from that annulus. And it turns out that if you are able to do this, then in that final puzzle piece W, you end up with an annulus in there. And so that when you take this infinite cone thing, those annuli stack together. And eventually, so at the moment, this is some infinitely long annulus, and then you do this one-point compactification, so you get yourself a disk. And so we used Quinn's result about normal bundles to see that that cone point V or infinity, that's a manifold point. We can apply the same result to this sort of pointy disk to see that that disk is locally flat. So basically, the argument that we sketched yesterday to construct this topological manifold, a similar argument will show you that Alexander polynomial 1 knots are topologically sliced, as long as you do this in the appropriate relative setting. I don't know to what extent you remember the statement of the theorem yesterday. In the case of codimension 2, there was an infinite cyclic group that came in, and that's where the Alexander polynomial 1 condition comes up. Not that important. Okay.
Wait, the pi1 of the complement is 1, not z?
This, do you mean
The annulus?
Do you mean this right here?
Yeah.
This is me writing it sort of poorly. The pi1 of the complement of the annulus would be something like z. This is meant to be pi1 of the whole thing. Notably, I did not tell you what
Okay.
pi1 of what. I didn't say anything like that. Yeah, one should work this out in proper details. But the slogan that you should maybe take home with you is that this construction done in the relative setting correctly will produce for you a locally flat slice disk for an Alexander polynomial 1 knot. But your point is well taken, though. There was an embedding step in here, which you're trying to do in the complement. And in fact, now you have to do that embedding step in a four manifold with fundamental group C. More on that later. Okay. Are there further questions?
So is this that you construct, then is this just the cone of the knot, or is something?
It's not. So that's a great point. So what I'm trying to do here, again, I'm not saying very many details, is right. So you started with your Alexander polynomial 1 knot, and you took its product with the interval inside of S3 cross interval at the moment. And then now you're trying to do this entire surgery process with the goal of making the complement of the disk have fundamental group Z. So now, like if you were not trying to do this in a relative way, you would have just constructed the cone on S3. But because you're trying to do this in the relative setting, you no longer just get the cone of S3, you get something a bit much more weird looking. So it's right, this is why I made this thing look a bit wiggly, because when you're doing this surgery, for example, in this last step, you've changed something. So this thing is not just the product, in case that's what you were wondering. Okay.
But couldn't then be the manifold you construct be something else than the ball? Or the C?
That's another very nice question, actually. So if it turns out that this, okay, I did not, let's not go back there. So it turns out that for an integer homology sphere, not only do you get a contractible four manifold, it's the boundary of, that four manifold is unique up to homeomorphism. So if you give me a contractible four manifold bounded by S3, it must be B4. And exercise, prove that using the Escaportism theorem. Relative Escaportism theorem, perhaps. Further questions? But that's a great question, though. Sorry.
Can I ask a quick question,
Of
maybe
course.
connected to something on a previous slide? When you were talking about the classification of the classification up to homeomorphism in the boundary case, and I think you were saying that we've known simply connected for a while, and then pi1 equals z very recently. If we restrict the boundary to being an integer homology sphere, do we then know this result for all good groups?
That's an interesting question. So this is another thought I used to have, that, so I promise we'll talk about grid groups later, in case you don't know what they are yet. But I sort of had the feeling that, okay, when the moment you know that a group is good, all the sort of things should follow, right? Like everything should just follow right after, because good group means that Friedman technology works. The classification does not come so easily. You have to like, there's more work to be done there. So in particular, this list is not just list of good groups. You need more in order to get a classification result.
But so in terms of what more do you need, is having a good group and an integer homology sphere boundary enough, or do you need more than just knowing that the boundary is an integer homology sphere?
I think you need more than that.
More than that, okay. Because I think the trick that I sort of have in mind is that, well, we can always cap off an integer homology sphere with a Friedman fake four ball, and then we'd be in the closed situation with a good group. So presumably the technology would run. But I'm guessing the problem.
But we don't know, for example, classification of closed four manifolds with good fundamental group. So that's also, so I mean, right, this list is for closed four manifolds. And for example, I did not just write all good groups. This is not the list of all good groups. There are more good groups, but there's like, one needs more.
Yeah, excellent. Thank you for the clarification.
You're welcome. But I think this is also worth noting, that there's this big open question about which groups are good, and we'll get to it. But that's not the end. Even if we knew, let's just assume that all groups are good, that doesn't mean that that's it, no more topological four manifold theory. That's not enough. Like there's more that, like, that's not the only question in this area. That's maybe what I want to say. Okay.
Great.
Maybe a slogan there is that a lot of the classification results come from techniques of surgery theory and modified surgery theory. And Mark, Powell, Patrick Orsen are great people to ask questions to about that stuff. So please do so. I'm going to continue on though, unless there are other questions. Other questions? Okay. Right. So this result of Alexander polynomial one knots are topologically sliced. The proof that I gave you is not the standard proof. I happen to like this proof, but there are others. There are at least two others by others. But this is a nice one related to things we've already seen before. There are some generalizations of this statement, notably results of Friedel and Teichner, which gives other constructions of slice knots in the case of a different fundamental group of the complement. And then you also heard something about shake sliceness from Allison on Monday. One can ask when topological slice disks are unique up to isotopy. Lisa mentioned there's work of Conway and Powell about this. And then there's also things you can say about two knots. So for two knots, the question is more about isotopy rather than concordance or sliceness. So for example, we know that two knots, spherical two knots with pi1z are topologically unknotted. So in this case, for example, this is kind of going in the other direction, like not in the other direction. This, for example, is, hey, smooth manifold topologists, go and find us, the smooth analog of this question, go think about that. And this is the context that's for those smooth results. And similarly, Lisa mentioned results about exotic disks and exotic surfaces inside of four manifolds. Well, questions like this are, results like this give context for that. Okay, so I'm going to stop listing results now. But kind of the motto of the results that I've stated so far is that, look, there are lots of things that we know in the topological category. If you're interested in topological four manifolds, I hope I'm trying to convince you that they're interesting. There's more that's there to be done. So it's not like finished by any means. Alternatively, one could try to think about the smooth analogs of these questions, or you look at the smooth results that you know and then see, well, what can we say in the topological category? So there's like this, one wonderful fact about four manifolds is that it's the first dimension where we see this disparity between smooth and topological settings. So this is why we should work in concert and not just off in our own rooms by ourselves. Maybe too soon to say something like that. Yeah, anyway. All right. Okay, so that is a long list of results. Let's change tack a little bit and think about, well, what do we have? So we talked about sort of big, powerful results and what went into the proofs of these things. So the first thing that we have is the Discombining Theorem. So I will get to the Discombining Theorem in a second. But what I find really, really cool is these four things that I've kind of grouped together at the end. And these came out of Quinn's work that we talked about in the live lectures. Okay. And so what these four results are kind of telling us is that working in the topological category doesn't have to be so hard. Like, in the 70s, it was really hard because we didn't know these things, but now we do. So if, for example, when Allison was talking about shake sliceness and, changing this perspective between the four manifold perspective and this perspective on knots, we were able to do that because we do have these powerful tools. And so I think an interesting question that we could all be asking ourselves is, well, when you prove a smooth result, to what extent is that actually purely a smooth result? Because some of these fundamental tools are in fact available in the topological category. And so maybe what you've proved actually holds in the topological category. And so that's a worthwhile thing to think about. Like, where exactly are you using smoothness? Like, this is what we did when we talked about the topological Escaportism theorem. We looked at this category losing result. We looked at like Friedman's original thing started with the smooth Escaportism and got a homeomorphism out of it. But then we noticed that, wait a minute, we didn't really need the smoothness. I'm not saying it was difficult to get these fundamental tools, but we have them now. So that's pretty cool. And that means that we may not be using the smooth category as much as we might think. So, right, so what did we do in the lectures? We had this flowchart, and we were focused on this part of it a little bit. So I spent some time talking about handle smoothing, and we saw that this is sort of a very nice framework across dimensions. And then that's how we got these three fundamental tools. And then once we had these three fundamental tools, it turned out that some of our results that seemed to require the smooth category didn't actually need it. So one thing I wanted to point out here, I don't think I stressed this very much yesterday, so I want to do it today. This result is work of Friedman, like I said. That's this key insight that goes into the Discombining Theorem. So that's, of course, sort of very central to this. And then this non-compact Escaportism theorem of Frank Quinn, that really leads to everything else. And now, I said nothing at all about what goes into the proof of a non-compact Escaportism theorem, but the idea of the proof is very similar to the proof of Friedman's Escaportism theorem. It's just that you have infinitely many disks, so you have to keep track of what's happening to all of those intersections, and you have to do things. You saw in the proof outline that we were doing things very explicitly. We were sort of pushing points around and tubing things and so forth. And if you have finitely many disks, this is not so bad because you just do them one at a time. And in the end, you fix all your intersections. But in a non-compact setting, you have infinitely many things that you have to push around. You have to make sure that you're not trying to make a disk move infinitely far away. And so this thing is difficult to prove. And like there's a lot of hard work that goes into this. Okay. So that's something I wanted to stress. Like, if the real heart of this work of Quinn is this non-compact Escaportism theorem, which admittedly I did not spend very long talking about, but that's the key technical thing that's going on in there. The next thing I wanted to show you is, again, I promise I'm not a conspiracy theorist, but this is it. So this is the work of Friedman. But to go from Friedman to, like, let's say, here's the classification of four manifolds, here's the existence of exotic R4s. There's lots of routes to these things, but there's just like this controlled Escaportism theorem that shows up over here. This entire left-hand side of the development, that's work of Quinn. Okay. Yeah, there was a time that Mark and I were just drawing this on various boards in various countries and offices, and I'm sure people thought we were having some sort of crisis, and perhaps they were right. But this is sort of the story of how, even if once you know that skyscrapers are standard, there's still work to be done to get to all of this other stuff. Again, the slogan is Quinn appreciation, so that's part of what's happening. Okay, please don't try to read all of this. Just marvel at its ludicrousness.
What are the colors for?
So this is an excerpt from this upcoming book project of 20 people. So look there for the key. The blue here are the fundamental tools that I've referenced. Green corresponds to inputs that are sort of outside of the Friedman and Quinn technology. Red are the category preserving results. So Discombining theorem, that's purely topological. Purple are the results that category losing, so smooth input, topological output. So there's a Poincare conjecture here that's purple like that too. And then the yellow ones, these are the landmark results. Like these are the things that you've perhaps heard of. It's like, yeah, that's like a big highlight of the field. In my mind, I have a dream that someday this will be like a clickable thing on a web page somewhere. So you would be able to like, you click on the classification of four manifolds and this will like light up all the different routes to it. So you'll know precisely what depends on what. But I promise, not a conspiracy theorist. No chemtrails were harmed in the writing of this talk. Okay. All right, let's try not to look at this for too long, or that will not. Okay, let's continue on. The thing I would like you to take away from this, though, is that, man, that thing was confusing, but people did it. Like, that's done. That's not something we have to do now. So these fundamental tools are available to us. And so, for example, something I think about often, recently I had a mild panic attack about, why do I know anything about topological concordance? So for example, topologically sliced, right? So a knot is topologically sliced. A knot is topologically sliced if it bounds a disk, like, whoop, not like that. So I want a disk like this, and I say that delta is locally flat. Oops. Okay. All right, but the first thing that I do when I think about a slice disk is often I consider the complement of it. Like I remove a neighborhood of that slice disk. That's like the first thing I've ever done with a slice disk, but all I know at the moment from this definition is that it's locally flat. So why does it even have a nice neighborhood? So I mean, even doing something like that, like removing a neighborhood of a slice disk, that's saying something about like, there's a normal bundle for that disk. And I needed Quinn to do that. And so for a long time, I heard that slogan that, oh, everything that, you know, this classical stuff, everything holds for topological concordance, but how did we know this? So I think this is a nice exercise to think about. For example, why does a topologically sliced knot have signature 0? Probably the proof that you saw used some sort of transversality. The good news, we have those things, okay? So we don't have to worry about that anymore. So no panic attacks are necessary. But we, you know, that stuff, when people did these things, they were working in the smooth category. But now that we have these fundamental tools, you can do a lot of this stuff in the topological category. So no panic attacks necessary. So maybe more things apply in the topological category than perhaps you thought of. Okay. All right. I promised you that I would tell you the Discombining Theorem in its full glory. So that's what's coming up next. Okay. So here's the full statement. The full statement starts off with a four manifold, which is topological, connected. So one thing I really love about this framework is that there are very few adjectives in there. And the only adjective that I really need is connected. And that's just because I want to talk about its fundamental group. And I want the fundamental group to be good. More on that in a second. So in its full glory, the input of the Discombining theorem is a collection of disks. So not just one, but finitely many. And so just like before, we'll have these finitely many disks. And on the boundary, I already have a nice flat embedding. And then we had our disks used to have these partners. There used to be just one, but now because I have many disks, all of them have these companion spheres. They're called algebraically dual spheres. Okay, so this is the input to the Discombining theorem. Now there are disks embedding theorem, and there are two inputs. There's the thing I want to embed, and it has these dual spheres that are going to help out. And then the output has two parts as well. First, there are analogs of the two inputs. The first thing is I have this F bar. That's an embedding of all of these disks. So this is a nice flat embedding. I should definitely write that. And on the boundary, this is the same. So this is the part that I'd already told you. And then the output has a second portion, those partner spheres that we put in to the hypothesis, they also have a geometric output. So there's a collection of spheres for these outcome disks, such that these disks and spheres, they intersect in this super nice way. So each disk has a sphere, an immersed sphere, that intersects it precisely once and none of the other disks. Okay, and then this last portion over here for pi1 non-trivial, this is due to Mark, myself, and Peter Teichner in 2020. So just a quick side note, there's a slightly more generalized version of this, which is also for, just compact surfaces. Which is due to Kaspersky. Okay, I apparently can't write today. Mark, myself, and Teichner. This is being written up right now, so that's 21 plus. Not really going to talk about that though. All right, so this is the Discombining Theorem in its full glory. I don't want to, certainly not going to talk about its proof at all. But hopefully this is reminding you of the preliminary version that you saw last time. Okay. I do want to talk about what are the ingredients that go into this. So one thing you probably noticed is that the manifold, the ambient manifold, is no longer required to be smooth, right? So this was purely in the topological category. So we're really using these three fundamental tools. Like we have these now, so let's use them. So we no longer need a smooth ambient space for this theorem. On the other hand, when so now I also have a non-trivial fundamental group. So in the recorded lectures, I just talked about intersections as being canceling when they have opposite signs. But now that I have non-trivial fundamental group, we have to count our intersections in a bit more general setting. And those are called equivariant intersection numbers. So I wrote some exercises about this in the typed lecture notes, so feel free to look there for more details. But here's sort of the idea of the proof, idea of the definition. If I have A and B, these are simply connected surfaces, A and B, inside of a four manifold, and I want to count its equivariant intersection form. What I do is I'm going to look at the base point of my four manifold. I have that intersection point P. I'm going to come up for you with an element of the fundamental group corresponding to that intersection point by starting at the base point, taking a loop over to A, going along A to the point P, going along P to somewhere in B, and then back to the base point somehow. So that little path that I drew over there, that's something I'm going to call gamma of P. And then this equivariant intersection form, this is going to be the sum over all P's in this intersection of the sign of the intersection point and that curve. So this is going to be an element in the group ring of the fundamental group of M at that base point. Let me avoid talking about the sign unless someone wants me to, then please ask at the end or in the chat. The advantage of this setup is that the vanishing of this number is precisely the question of when these intersection points of A and B can be paired up by maps of Whitney disks. So framed immersed Whitney disks somewhere in that four manifold. And then the self-intersection number can be defined in a similar way where that thing vanishes precisely when these self-intersection numbers are paired up in this way. And so if you sort of go back and think about the sketch of the proof of the Discombining Theorem, this is the only thing that we needed, that whenever you have these intersections sort of canceling, that we got these Whitney disks. So now we just have to count it in a different way, but the result is still the same. Okay. So that's something we needed for this. The other thing we needed was this notion of what is a good group. So let me spend some time talking about what that is. This definition is kind of, I'm sure it seems extremely random, and it is. It's essentially the thing that makes the proof work. Okay, so that's not very useful unless you've spent a lot of time thinking about the proof. But here's what it says. First, we want to know what a height 1.5 capped group is. It's something that looks like this thing in the bottom left. So we saw what groups are in the recorded lectures. So here's a quick reminder. So a group of height 1 is just a compact surface. So in this case, it's a compact surface. It's that one. A height 2 group would have more surfaces attached to a symplectic basis of curves for H1 of that base surface, but I just have height 1.5. So I only get a surface on 1/2 of those. Okay, so that's why. So far I've talked about the group part and the caps. Those are precisely these disks that are attached to now these remaining curves on these surfaces. So here's 3 of them. I've drawn sort of a simple example. These caps can intersect themselves, each other, some more, there can be more genus, etc. So this is just an example of a height 1.5 capped group. One thing that's very important here is this warning that I've only really drawn for you the 2-dimensional spine of this thing. So there are really 4 manifolds, so you should think about them as being thickened versions of this thing. And then we say that a group gamma is good if whenever you have a creature like this, a GC, and you have a homomorphism from its fundamental group to that group gamma, there should be an immersed disk inside of that capped group with the same attaching region. The attaching region is here in purple. So I want there to be some immersed disk like this with that purple boundary. It's a 4-manifold, so finding that immersed disk is a meaningful notion. So finding that disk is not bad, but I need to look at these double point loops, these loops that start at the self-intersections and travel around. These generate the fundamental group of this object. And I want these things to map to the trivial element under this homomorphism phi. Okay, so if you think this is a ridiculous definition, you're not the only one. It seems very random, like why should that be the definition? Well, the thing is, it's just, this is the thing that you need in the proof. Okay, so that's where that's coming from. That's perhaps not very satisfying. I'm not sure what to say about that. But I do want to say one thing, which I find kind of cool. This question of which groups are good, this is a pretty big deal. Like if we knew that all groups are good, okay, we won't solve topological 4-manifolds, but that would be a lot. That would be a pretty amazing deal. There's nothing really topological about any of this though. Yeah, like height 1.5 capped group, that's a smooth 4-manifold. Okay, it's a smooth 4-manifold, and I'm asking for a smoothly immersed disk, and I'm asking for something about its double point loops. At no point did I say anything about the topological category. Okay, and so I find this really neat that, you know, this knowing which groups are good is going to be a really big deal. But I mean, this is a question about the smooth category. Okay. So this is what I mean that like smooth manifold topologists can have a lot to say about this topological category by thinking about this problem. Okay. All right. So this is a purely smooth notion. What do we know about this so far? We know that the infinite cyclic group, finite groups are good. The class of them is closed under certain operations, so that's nice. And then the most that we know is that groups of sub-exponential growth are good. We don't know that all groups are good, and because of what I wrote in the top there, if we knew that the free group on 2 generators is good, then we would know that all groups are good. And it's a reasonable conjecture, one that's like, you know, plausible to be within reach, is whether amenable groups are good. But not all groups are known to be good. Many are, but not all. Okay. Right. So I wanted to spend some time talking about conjectures in this area. This really is just about like in this Friedman-Quinn machinery, in this world, what are some big things that are left? So I hope I've convinced you that the Discombining theorem is a big deal. And the Discombining conjecture is that it holds for all fundamental groups. Okay, so we don't know that. We only know that it holds for good groups. And conjecture G, I'm going to give these some letters in the hope that that helps. This says that every capped group of height 1.5 contains a flat embedded disk with the same attaching region. So if you remember the definition of a good group was instead of a flat embedded disk, I would have asked for an immersed disk with some sort of property. But in particular, if every capped group has a flat embedded disk, then that implies that all groups are good. So good groups and capped groups naturally very related. So, I mean, this implication comes directly from the definition. So if we knew that conjecture G holds, all groups would be good, and then you would have the Discombining conjecture. But then it turns out the Discombining conjecture, well, it's a question about when are there disks? And so it turns out that if you knew the Discombining conjecture, we would be able to, in particular, find that disk. So this is the circle here. Okay, so this thing about capped groups, that's equivalent to the Discombining conjecture. This is not a purely smooth question because this is asking for a flatly embedded topological disk, but that's different. But one thing that I do know is that capped groups are smooth four manifolds, so in particular, they have Kirby diagrams. These Kirby diagrams are not so difficult to construct. Like capped groups are built out of these surfaces and self-plumbed disks that are glued on top of one another in a pretty systematic way. And so if you look at each of these pieces have very nice Kirby diagrams. So for example, if I look at this surface, just the torus, thickened, of course, so there's a cross D2 happening there. This attaching circle I've shown in purple on both sides. And then this manifold is just given by this diagram. And so, you know, this purple thing is not part of the diagram, that's just a circle in its boundary. So if I just forget about this, you'll see that this is the unlink with dots on it, two component unlink. And this is not so surprising because the punctured torus cross D2, that's the boundary connected sum of S1 cross T3 with itself. So this is not so surprising once you know what all of the things mean. And then similarly, if you have the self-plumbed disk, this has the Kirby diagram of this form. I think I've detected an error in this picture, so let me correct it by doing that. So the clasp of this little whitehead curve, that corresponds to the sign of this plumbing. That's what it is. A great source for this sort of stuff is this wonderful book of Gompf and Stipschitz. So if you're learning about Kirby diagrams, that's the place to go. But of course, a capped group is something more complicated. To build a picture of a capped group, I should take those pieces and glue them together somehow. So for example, if I have this capped group of height 1.5, it will have a Kirby diagram like this. And then this circle, M of L, that's the thing that was drawn in purple before, that's the attaching region. So right now, this is a picture of a capped group. And this is a picture of its attaching region. And the question we're asking is whether that attaching region is the boundary of a flat embedded disk in this four manifold. Right? So this is a question about, is this not slice in this four manifold? topologically. And if I knew that, then I'd be done. That would be pretty amazing if we could show that. So right now, this is a question about slicing a knot in a complicated four manifold. Not that complicated, but certainly not a very pleasant picture. But we can also translate this to a question about sliceness of knots and links in a more general setting. So we can define this family MathCal L1 to be the links that you get as Kirby diagrams for height 1.5 capped ropes. They'll have these marked components corresponding to the attaching region. And the conjecture L1 asks, well, this says that every link in this family is topologically sliced in V4, where the slice disks for the not attaching curve are standard, meaning that this, if you like remove the attaching circle, you're going to get an unlink, and standard means that those are the disks coming from the standard unknotted disks inside of S3. This is just a reformulation of the fact that we had dots on those circles. Right? Like that was our interpretation of that dotted circle notation for one handles. That's where this is coming from. So to complete our picture from before, this is telling us that this conjecture L1 is equivalent to the conjecture G. So this is where the knots and links come in. So this question about slicing knots and links, this is precisely related to this discombining conjecture, which is going to tell us a lot about topological form manifolds. It's not everything, but quite a bit. Then finally, I wanted to wrap up by talking about two things that I did not really discuss very much. One thing is the Escaportism Theorem. Yes, Escaportism Theorem is a non-simply connected version of the Escaportism Theorem. So that's very easy to look up, so please feel free to do so. There's also something called surgery theory. Allison mentioned this in her talk. One can spend hours talking about this, so I won't, at least not now. But this is something, both of these are extremely powerful tools in high dimensions, and the Discombining Theorem allows us to use them in the topological category in dimension 4. And then, as always, there's a restriction to good fundamental groups for this. Okay. So feel free to ask more about this later, but I won't continue with it right now. But one cool fact is that these big results of surgery theory, they work in dimension 4 without restriction to good groups, precisely if a certain family of links in S3 are freely sliced. Freely sliced meaning the fundamental group of the disk complement is a free group. And now here below, I've given you the definition of what a good boundary link is. It's a boundary link. In particular, that means its components bound disjoint Seifert surfaces. And it's good if the kernel of a map of this form has perfect kernel, the kernel is perfect. That's a bit difficult to digest for the first time, but a reasonable thing to think about is that it's the link theoretic analog of knots with Alexander polynomial 1. So Alexander polynomial 1 knots are sliced, they're freely sliced, their sliced disks have complementary pi1z. But if we knew that these more general things are freely sliced, then we would know that this extremely powerful thing from high dimensions, that also works in dimension 4. And so here's a good boundary link. This is sort of the nicest one. This is the Whitehead double of the Bing double of the Hopf link. It's Whitehead, Bing, Hopf. So all your favorite links are in there. And this is the first good boundary link in under some metric. And we don't know if it's topologically sliced. It's not smoothly sliced. Adam Levine showed that. If all of those clasps are positive, that's the thing he did. But that's it. Prove that this thing is not topologically sliced. Disprove the surgery conjecture. Acquire fame and fortune. That's a life strategy. Okay. Let me end there. Thank you for your attention.
Let's thank Aru for a great talk and actually a great lecture series. So we have time for a question or two. Are there any questions?
Do you expect all groups to be good, or maybe it's a bad question?
It's hard to have an intuition for it because the definition is so random. I think that's where I stand on this. I think it's reasonable to expect amenable groups to be good. And I think, you know, these proofs that groups are good, those are very geometric, and they kind of, you know, I showed you this thing called contraction and push off, and I mentioned a thing called group height raising. And the proofs that these groups are, that certain classes of groups are good, that just comes from doing these geometric operations in a clever way. And amenable groups are sort of close enough to groups with sub-exponential growth that one expects that that sort of cleverness might be extendable. But in total generality, I don't know that people have ideas exactly. I can tell you, I wish that all groups were good, because I find the dichotomy of the topological and smooth category in dimension 4 to be quite aesthetically pleasing. But I'm not basing that on any mathematical thing, just that I think that would be lovely if that were true. Sorry for the non-mathematical answer.